Hello, everyone. My name is John Capece, and I've been involved with the Florida Democratic Party since 2004, and I currently serve as science officer of the Democratic Environmental Caucus of Florida, as well as its past president. I'm also president of the new Democratic Agricultural Caucus of Florida. My degrees are in agricultural engineering from the University of Florida, where I also served as a professor working on water quality issues years ago. After leaving UF, I continued to host university students for research project work from 1999 to 2020. I hosted more than 500 university students from 75 nations as full-time interns for programs from 2 to 12 months. And together we worked on technical topics like what we'll be discussing here today. I want to talk about an important aspect of what should be our climate strategy, specifically regenerative agriculture, and how we can effectively integrate it into the core democratic agenda. Let's begin by describing what we mean by regenerative agriculture and a related term, carbon farming. So, what is regenerative agriculture? A simple definition would be those farming methods that actively restore our soil, nature, and human health. It's a holistic, ecosystem-wide approach to working with the land rather than against it. Next, how do we define a similar term, carbon farming? Well, carbon farming refers specifically to farming methods that sequester atmospheric carbon dioxide into the soil, into on-site biomass, and into agricultural or forestry products for long-term storage. The explicit overarching goal here is to reduce climate change by removing CO2 from our atmosphere and locking it away safely. So how do the two differ? Well, carbon farming has much more limited goals and benefits than a comprehensive regenerative agriculture system. Because carbon farming focuses heavily and sometimes exclusively on the single metric of carbon removal from the atmosphere using agriculture, it has the potential to create unintended collateral impacts. Regenerative agriculture, on the other hand, factors in biodiversity, water cycles, and overall human health, ensuring that our environmental fixes do not inadvertently cause new ecosystem strains. This presentation focuses on regenerative agriculture and carbon farming. Why? Because the climate crisis is not an abstract, distant issue. It's a stark reality that has the potential to kill large numbers of us in future decades, and it threatens to submerge large tracts of Florida within the coming century, basically destroying our coastal cities. To understand the role agriculture plays in the climate crisis, let's look at three basic numbers. First, how much greenhouse gas do we emit globally each year? That number is between 50 and 55 gigatons of carbon dioxide equivalent per year. Second, how much of that massive footprint comes directly from agriculture and the land use changes associated with it? That number is 11 to 13 gigatons of carbon dioxide equivalent. And this is from the direct farming practices and land clearing for farms and ranches. It represents roughly 22 to 24% of global emissions. But if we expand our view to include the pre and post harvest production supply chains, that agricultural footprint jumps to over 30% of the global total. Third, how much of this can be offset if we aggressively deploy carbon farming? An ambitious estimate of the answer to that question is 5 to 20 gigatons per year, or 10 to 20% of our total global emissions. Agriculture is a massive part of the problem, but it clearly represents an equally massive piece of the solution. Let's visualize those numbers through historical data tracking global greenhouse gas emissions from 1990 through 2018. It's a little disappointing that data tracking has diminished in recent years. It's getting harder and harder to find current estimates of various climate-related metrics. But when we split the available data by sector, the largest single driver is energy at 34%, and it's followed by heavy industry at 24%, and right behind those two is agriculture and land use, which sits at 21%. Transportation is at 14%, and buildings constitute the remaining 6%. Our climate conversations typically focus on electric vehicles, replacing coal plants, or retrofitting buildings. And while those sectors are absolutely vital, agriculture and land use is a larger emitter than the entire transportation sector. If our climate agenda completely ignores the land beneath our feet and how we grow our food, we're fundamentally missing a major part of the entire global crisis. Now that we know the scale of the challenge, what do these practices actually look like on the ground? Regenerative agriculture is not a single silver bullet. Rather, it's a set of diverse land management tools. Its key methods include minimizing soil tillage to protect underground soil structure and biological systems, utilizing cover crops year-round to keep the soil anchored, and employing diverse crop rotations to break pest cycles naturally. It also involves managing livestock grazing for the purposes of mimicking natural herd movements. Another element is the production of biochar and its precise application or injection into the soil. We must recognize that the exact set of methods differs for every single combination of crop and regional landscape. What works for citrus grove in Florida will be different from what works for a wheat field in Kansas. Therefore, moving towards regenerative agriculture requires serious long-term research to develop a variety of localized farming systems that reliably deliver carbon storage and ecosystem health. Honestly, this is the sort of work that our universities, land grants institutions, our USDA labs, and our regional NRCS offices should have been doing for the past several decades. Instead, due to competing priorities and industrial lobbying, they're only now beginning to scratch the surface of this research. Pushing funding and expectations into these public research institutions needs to be a top political priority. Now, agricultural greenhouse gas emissions from agriculture include carbon dioxide, methane, and nitrous oxide. The biological and chemical mechanisms that govern the absolute quantities and the relative quantities of each of these are highly complex. And when you add in how industrial agriculture affects various parts of these processes, it becomes even harder to develop effective economical farming systems that will minimize these emissions while also maximizing the carbon intake into the soil. When we look across the globe to see where we can realistically store carbon using these methods, the total potential adds up to around 14 gigatons of carbon dioxide equivalent per year. This is within the target range of 5 to 20 gigatons. Understand, however, that estimates vary widely. Some believe that sequestering 5 gigatons is extremely ambitious, while others think 4 times that is achievable. We really won't know until we actually get serious about trying. But managing our global grasslands can sequester roughly 1 gigaton per year. However, this pool remains highly vulnerable to wildfires. Agroforestry, which involves combining trees and shrubs with other agricultural crops and livestock production, has a potential of over 3 gigatons. Direct soil carbon sequestration can capture around 3 gigatons as well. Finally, standard forestry practices and optimized timber harvesting hold the single largest potential at over 6 gigatons per year. We must take into account the risks. Grasslands, agroforestry, and traditional forestry all have high vulnerability to fires. Fires like those ravaging Europe right now, and like those in our country that we face each year. As global temperatures rise and extreme wildfire seasons become the norm, carbon stored exclusively in above ground biomass like tree trunks and leaves can easily go up in smoke, instantly re-releasing those greenhouse gases back into the atmosphere. This risk makes direct soil carbon sequestration all the more attractive. So we must take these risks into account. There are other risks we have to take into account. And so while carbon farming solutions sound wonderful in theory, a responsible, science-driven approach must acknowledge some potential problems and unintended consequences, especially those associated with biochar. First, with biochar, there's the risk of re-release. Not all biochars are created equal. Certain types can decay much faster than anticipated, releasing greenhouse gases right back into the atmosphere. Second is the energy footprint. It takes a significant amount of thermal energy to produce biochar. And if that energy isn't carbon neutral, it partially negates the intended climate benefits. Third, biochar can significantly alter soil pH, pushing alkalinity upward and inadvertently undermining microbial and plant growth. Fourth, depending on the source material used, some biochars have been found to be heavily contaminated with toxic substances. Fifth is nutrient disruption. Biochars act like a sponge. They can tightly grip the nutrients that plants need, and this can drive farmers to apply even more chemical fertilizers to compensate for this. And finally, we have to worry about micro and nanobiochar. As biochar naturally breaks down over time, it can create small particles that mobilize some contaminants and can threaten human health. So while biochar can support agriculture, uh, we cannot treat it as an unmitigated fix. It requires careful oversight. Because of the risks associated with biochar, regenerative agriculture prioritizes cultivating living carbon over injecting dead carbon. We can achieve this stable living carbon sink through two primary methods. First, continuous cover cropping. By keeping the soil covered with a diverse mix of live plants year round, we maximize photosynthesis. These plants actively pump liquid carbon in the form of natural carbohydrates down through their roots and to feed hungry soil microbes. These microbes, in turn, process these sugars and convert them into stable, deeply buried soil organic matter. Second, no-till and low-till farming. When we eliminate mechanical soil disruption from plowing, we preserve underground fungal networks, and these beneficial fungi naturally secrete an incredibly stable natural carbon compound that keeps carbon securely locked deep in the soil for decades. But as we gear up to invest in regenerative agriculture, we must also take other easier steps to reduce our climate impacts. We need to change which foods we choose to eat. Our diet leaves a massive environmental footprint. Beyond the direct greenhouse gas emissions from production and shipping, we know all too well how farming affects water through irrigation demands and runoff pollution. And of course, there's pesticides and other chemicals. Consumer demand drives all of these negative impacts. Therefore, systemic agricultural reform and cultural dietary shifts are deeply intertwined. So let's look at the numbers regarding how different food choices stack up against one another in terms of greenhouse gas emissions. This first chart shows the greenhouse gas emissions generated from the foods based on their protein content. These differences by food type are quite dramatic. Beef generates a staggering 50 kilograms of emissions per 100 grams of protein. Lamb and mutton follow at nearly 20 kilograms. Farm shrimp carries a high climate cost due to its mangrove destruction and methane generation. And as we move down past pork, we find lab-grown meat at 6 kilograms, farm fish at 6, and poultry also at 6, with eggs at 4. At the bottom of the chart are the plant-based proteins. Tofu drops down to a mere 2 kilograms. Beans and peas come in at an incredibly low 1 kilogram, and nuts represent a virtually microscopic zero point 0.3 kilograms of emission per 100 grams of protein. Reducing or producing 100 grams protein from beef generates roughly 60 times the greenhouse gas emissions of producing the same amount of protein from beans or peas, and nearly 200 times that of nuts. When we talk about low carbon targets, reducing our reliance on livestock is the lowest hanging fruit available. If we look at our foods from not from their protein perspective, but from simpler caloric energy content, we see basically the same relationship. Beef remains the highest emitter by far. As we look at the more efficient lower end of the spectrum, eggs require less than 4 kilograms and meat requires less than 3. When we jump down to the crops, rice requires about 1, oats and wheat under 1. Legumes represent the ultimate caloric efficiency, generating less than 1 kilogram of emissions per 1,000 calories. Whether you're counting protein or counting calories, shifting away from beef and towards plant-based alternatives is mathematically the most powerful dietary choice a climate-conscious citizen can make. So let's translate these numbers into consumer behavior by looking at average U.S. food consumption habits versus what would be a healthy, climate-friendly goal. Right now, the average American weekly diet is dangerously out of alignment with low carbon targets. For example, Americans currently eat roughly 730 grams of beef per week, which is 7 times the recommended maximum low carbon targets of 0 to 100 grams. We eat about 40 grams of pork, which is 4 times the recommended target. We consume roughly 900 grams of chicken and poultry, which represents 3 times the low carbon target. Conversely, we consume only about 140 grams of fish and seafood, which is half of what a climate-friendly target suggests. Most shockingly, our consumption of legumes is currently completely negligible, averaging under 50 grams a week, which is a pathetic 0.1, 10% of the ideal target of 700 to 1,000 grams. A realistic carbon-friendly weekly protein diet doesn't mean forcing everyone to become strictly vegan overnight. A substantial weekly baseline can include 300 grams of chicken, 300 grams of fish, 50 grams of pork, 50 grams of beef, alongside the 100 grams of legumes. This is a balanced, achievable target that we can achieve actively by promoting public health campaigns and education. Now that we have covered the core agricultural science and cultural shifts in consumer eating habits, let's pivot into policy and law. How do we actually support the implementation of regenerative agricultural practices? To answer this, I want to share the findings of a 2024 Masters of Science thesis completed at the University of Florida by Roch Abu-Jaude Jr. I worked with Roch to develop and implement this research project. Some of you know Roch. He was the 2020 Florida legislative Democratic candidate for District 10 and the 2024 Democratic candidate for Congressional District 12. Right now, Roch is, I think, on a plane. I don't think he's landed yet, but he's heading far overseas, like 10 time zones or so, to begin work on his climate-related doctoral research. Well, Roch's 2024 master's thesis is titled Evaluating State Legislation for Carbon Sequestration Through Targeted Agricultural Incentives. What Roch did was to review every single piece of agricultural and carbon farming legislation introduced across all 50 states over a 17-year period. He evaluated thousands of bills against a set of criteria we developed to assess how closely those bills approached what we considered to be the ideal legislation. According to our analysis, there are 5 key criteria that defined ideal state-level policy. It's basically the filtering process we use to narrow it down to the best legislation. First, to select the overall pool of legislation, the bill language needed to address carbon farming or regenerative agriculture. These bills typically mention some keywords like soil, carbon sequestration, agriculture, etc. Second, Roch looked to see if the legislation provided tangible subsidies or financial incentives specifically earmarked for these practices or funding the research into developing regenerative agricultural practices. Third, Roch identified those bills that provided financial subsidies directly to farmers rather than being swallowed up by middlemen or bureaucratic administrative overhead. Fourth, the ideal subsidies would be directly tied to quantitative measures. This establishes a pay-for-performance model, ensuring that public taxpayer dollars are only handed out when real, verifiable environmental productivity is being accomplished on the land. Just as farmers get paid for their products they deliver to market, so too would climate productivity be measured. Fifth, and most importantly and most elusive, subsidies should be based directly on actual soil carbon measurements. Measuring the actual organic carbon locked in the dirt is the ultimate goal of this entire policy movement. If a bill does not include real soil testing, we cannot verify if it is working. Now, keep these five criteria in mind as we look at the historical data on what has actually passed state legislatures. When we look at the historical timeline of state level bills passed from 2009 through 2025, the trend line tells a deeply concerning story. The passage of regenerative agriculture state bills was very late in starting, slow in growing, and has now, unfortunately, nearly shut down entirely. The top chart tracks all 193 pieces of legislation that passed, separated into binding statutes and non-binding resolutions. For years, passing anything was a struggle, averaging under 10 bills a year across the entire country. But we saw a massive encouraging spike in 2021 with over 35 bills enacted, followed by a strong showing in 2023 with nearly 30 bills. But look at 2024 and 2025. Passage plummeted to a crawl. The bottom chart filters for quality by tracking only the comprehensive bills that met 4 or 5 of our ideal policy criteria. The view is incredibly bleak. In most years, the number of high quality bills passed across the entire United States was 0. The peak occurred in 2023 when a grand total of only 5 comprehensive bills passed. By 2024, that number dropped to 0. And 2025 saw only a single high quality bill enacted. We're not just losing momentum, the legislative engine has essentially ground to a halt. Now, this is not rocket science, folks. I personally recall how these methods were being promoted as climate essential solutions as far back as the mid 1980s. The no-till farming movement began in earnest in the USA with the establishment of the National Soil Tilth Lab at Iowa State University, where I studied in 1985 and 1986. States should have begun widely adopting regenerative agriculture and carbon farming legislation by the 1990s, not starting 20 years later. Let's next look at how these data map out geographically across the nation. This map shows which states adopted any carbon farming bills, and the number in parentheses shows the number of bills that met all 5 of our ideal criteria. Nationally, only 22 states managed to pass at least one bill containing one or more of our criteria. California is the overwhelming leader in pure legislative volume, passing a massive 75 bills, though only one California bill met all 5 criteria. Other active states include Washington, Colorado, Hawaii, Illinois, and New York. But the most critical takeaway from this geographic data is the text on the right. Only 6 states in the entire country have ever passed a bill that meets all 5 of our criteria. Those 6 leading states are Washington, Oregon, California, Hawaii, Colorado, and Minnesota. Now let's take a look at Florida. Florida is completely grayed out on this map, sitting at zero. So despite being a major agricultural state and despite facing catastrophic existential threat of sea level rise, Florida has passed exactly zero bills supporting carbon farming or regenerative agriculture. This is a massive, unacceptable policy failure that we must fight to correct. To understand why we see this massive geographic disparity in agricultural policy, let's take that legislative map and compare it directly to a U.S. electoral map from a few years ago. As you look at this visual breakdown, the political dividing lines are instantly recognizable to anyone who follows American elections. We see the familiar blue blocks across the West Coast, the Northeast, and parts of the upper Midwest, representing Democratic strongholds. Conversely, we see massive bands of red across the South, the Plains states, and the Mountain West. The graphic was actually lifted from a newspaper cartoon, which explains that the red states are humorously classified as weird. But the underlying policy point is deadly serious. Environmental policy has become deeply, intensely tribalized in this country. Practices like carbon farming, which should be viewed as common sense, bipartisan tools for economic resilience and soil health, are frequently painted as strictly partisan issues. Let's next overlay these two maps directly to see how tightly agricultural policy aligns with standard partisan identity. When we overlay the data, we discover a stunning 90% agreement between a state's legislative map for carbon farming and its traditional political map. The partisan alignment is nearly absolute. Let's look at the specific breakdowns. There are 19 states highlighted in green that are either solidly Democratic or swing states that have actively passed carbon farming legislation. On the flip side, there are 26 states colored in red that are solidly Republican or red-leaning swing states that have completely lack any carbon farming legislation whatsoever. The exceptions to this trend are incredibly small. We see only two Democratic-leaning states that lack legislation. They're colored in dark blue, and those are New Mexico and Delaware. Conversely, there are only three Republican-controlled states, Utah, Colorado, and Ohio, that buck the partisan trend and pass carbon farming legislation. They're highlighted in orange. This 90% correlation proves that carbon farming is currently trapped inside our national partisan gridlock. In red states, environmental bills are often dead on arrival, while in blue states, they can find a path forward. As Democrats, we have to recognize this reality. If we want to rebuild our soils and salvage our climate, we must find ways to break through this tribalism, framing regenerative agriculture not just as a climate fix, but as a vital economic lifeline for rural farmers everywhere. Or we could solve the political dimensions of the problem by simply winning a lot more elections. I want to conclude by bringing the focus back to the core challenge of integrating regenerative agriculture deeply and permanently into the active democratic agenda. The science we examine today is clear. Our current industrial food system is a massive driver of global greenhouse gas emissions. Yet by scaling up natural biological systems like continuous cover cropping and no-till farming, we can transform our soils into one of the most powerful, stable carbon sinks on Earth. But to unlock this potential, we must act across two distinct fronts. As individual consumers, we must take personal responsibility for our own climate footprints by consciously shifting our consumption habits away from high emission foods and towards highly efficient plant-based proteins and calories. More importantly, as political organizers, we must break the current legislative stagnation. We need to aggressively champion state and national level bills that provide real, direct, performance-based subsidies to our farmers based upon actual soil carbon measurements. We cannot allow common sense soil health to remain trapped in a 90% partisan gridlock while our home state faces the existential threat of being submerged by sea level rise. It is time to mobilize our communities, update our policy platforms, and ensure that we truly think green and vote blue. Thank you very much for your time and attention.